What is exactly the observable universe? The observable universe refers to the portion of the universe that we can observe and study using telescopes and other instruments. However, this capability is limited because light, the main source of information about the universe, can only travel at a finite speed. As a result, we can only observe objects or events that are at a certain distance from us. We cannot directly see objects or events that occurred long ago in the past. The observable universe refers to the portion of the cosmos that we can study using telescopes and scientific instruments. But our ability to observe it is fundamentally constrained by the speed of light, the universe's ultimate speed limit. Because light takes time to travel across the vast expanses of space, we can only see celestial objects whose light has had enough time to reach Earth. This means there are regions of the universe that may be full of galaxies or other structures that remain hidden from us simply because their light has not yet arrived. In this sense, the observable universe is both a vast domain of exploration and a natural boundary to our current understanding. Its diameter is estimated to be about 93 billion light-years, far exceeding the universe's age of 13.8 billion years. This apparent contradiction is explained by the constant expansion of space itself. As the universe expands, objects that were once relatively close become farther apart, and the light they emitted long ago has taken much longer to reach us, allowing us to observe regions now much more distant than might seem intuitively possible. Despite these inherent limitations, the observable universe offers an extraordinarily rich area for scientific study, and our knowledge of it continues to grow thanks to breakthroughs in technology and the deployment of space-based observatories such as NASA's James Webb Space Telescope. These advanced instruments have greatly improved our ability to explore the structure, composition, and history of the universe. They have provided invaluable data about phenomena that occurred billions of years ago, giving scientists unprecedented insights into how galaxies, stars, and other cosmic structures formed and evolved. Among the James Webb Space Telescope's most groundbreaking capabilities is its ability to peer back into the universe's earliest epochs by detecting faint infrared light from ancient galaxies. By analyzing this light, researchers can observe celestial bodies as they existed just a few 100 million years after the Big Bang, effectively giving us a glimpse into the universe's formative years. This ability to observe the distant past is largely possible because of a phenomenon known as redshift. As galaxies move away from us due to cosmic expansion, the light they emit is stretched into longer, redder wavelengths. The James Webb Space Telescope is specially designed to detect these wavelengths, enabling astronomers to study galaxies that are not only incredibly far away, but also existed when the universe was still in its infancy. These observations have provided critical information about the rate of star formation in the early universe, helping scientists understand how the first stars ignited and how early galaxies evolved. Understanding the conditions under which stars formed and galaxies took shape during these early epochs is essential for constructing accurate models of cosmic evolution. One of the most compelling aspects of exploring the observable universe is the possibility of discovering extraterrestrial life. For centuries, humanity has wondered whether life exists elsewhere in the cosmos. Recent advances, especially the discovery of exoplanets, planets that orbit stars beyond our solar system, have made this possibility seem increasingly plausible. Scientists have used methods such as the transit technique and radial velocity measurements to identify thousands of these worlds, some of which bear striking similarities to Earth. These planets are considered prime candidates in the search for life, especially those located within the habitable zones of their stars, where conditions might permit the presence of liquid water. A particularly intriguing discovery by the James Webb Space Telescope was its detection of water molecules in the atmosphere of an exoplanet called WASP 96b. Though this planet is not considered Earth-like in its broader characteristics, the finding of water vapor clouds and haze was unexpected and significant. These features challenge existing assumptions about which kinds of planets might support life, or at least the building blocks for it. Water's presence is one of the most crucial factors in assessing habitability. And this discovery adds to the growing body of evidence suggesting that potentially life-supporting environments may be more common than once thought. As we continue to study the observable universe, profound questions remain about what lies beyond it. By definition, the observable universe is constrained by the distance light has traveled since the Big Bang. However, it is widely believed that the total universe extends far beyond this limit. Some cosmologists estimate that the universe could be at least 10 to the power of 23 times larger than the observable portion, a staggering possibility that emphasizes how much remains beyond our observational reach. Since we cannot directly observe these distant realms, we can only theorize about what might exist there. One of the most fascinating ideas to emerge from such speculation is the theory of the multiverse. This hypothesis suggests that our universe might be just one of many, perhaps even an infinite number of parallel universes existing simultaneously. The idea has some support in quantum physics, particularly in interpretations that challenge the classical notion of a single deterministic reality. According to the many worlds interpretation of quantum mechanics, every possible outcome of a quantum event actually occurs in its own separate universe. In this view, what we perceive as random outcomes are in fact different branches of reality playing out in parallel. While still speculative and lacking direct empirical evidence, the multiverse theory has captivated scientists and philosophers alike. Some proponents argue that it could help explain the finely tuned physical constants of our universe, which seem to be just right for the existence of life and matter. Others are more skeptical, seeing the multiverse as an elegant but untestable idea with our current technology. In addition to the multiverse, another enigmatic phenomenon that has stirred scientific interest is known as dark flow. First proposed in 2008, dark flow describes the unexpected motion of galaxy clusters moving faster than predicted by existing models of matter distribution. The hypothesis suggests that some clusters might be influenced by a gravitational pull from a massive unseen structure beyond the observable universe, implying the presence of unknown matter or a deeper cosmic structure that exerts an influence on the visible universe. Some researchers have linked dark flow to the effects of dark matter and dark energy, two of the most mysterious components of the cosmos. Dark matter and dark energy do not emit light or radiation, making them extremely difficult to detect directly. Yet they are thought to comprise the vast majority of the universe's total mass and energy. While dark matter helps explain the gravitational behavior of galaxies and galaxy clusters, dark energy is believed to be responsible for the universe's accelerated expansion. The study of dark flow aims to determine whether these invisible forces account for the peculiar motion of cosmic structures, but the scientific community remains divided. Some studies support the existence of dark flow and propose explanations involving vast gravitationally significant structures beyond the observable horizon, while others question these findings, suggesting that the apparent motion might result from errors in data collection or interpretation. Regardless, the investigation into dark flow continues, underscoring how much remains unknown about the forces shaping the universe. The pursuit of understanding the observable universe and what may lie beyond it inspires profound questions and relentless inquiry. From mapping ancient galaxies to studying the atmospheres of exoplanets and contemplating the existence of parallel universes, the search to understand our place in the cosmos is far from over. Each discovery, whether it involves the distant past or speculative futures, expands our understanding of a universe that is as mysterious as it is vast. The technologies and theories developed along the way not only advance science but also broaden our philosophical horizons, prompting us to reconsider the nature of existence, the possibility of life beyond Earth, and the ultimate fate of everything we see. In the end, the observable universe represents more than just a field of study. It is a window into the unknown, a canvas of light and time that stretches the limits of human imagination and ingenuity. As we develop new instruments, refine our theories, and push the boundaries of observation, the universe continues to reveal itself layer by layer. Whether we eventually discover life on distant worlds, confirm the existence of other universes, or uncover new cosmic phenomena, the journey of exploration ensures that the mysteries of the universe will remain a source of wonder and discovery for generations to come. As our understanding of the observable universe deepens, the questions that arise become more complex and profound. The boundary between what we know and what remains unknown keeps shifting, shaped by new discoveries and the evolving capabilities of our instruments. The more we learn, the clearer it becomes just how much remains hidden. From the intricate details of dark matter and dark energy to the very shape and destiny of the universe itself. Scientists are not merely cataloging celestial bodies or measuring distances. They are trying to decipher a vast cosmic story that spans time and space, one in which humanity occupies only a small but increasingly aware part. One area of ongoing interest in cosmology is the geometry of the universe. The observable universe appears to be flat, meaning that parallel lines never converge or diverge over cosmic distances, an observation supported by measurements of the cosmic microwave background radiation from missions such as Webb and Planck. A flat universe implies that it will expand forever, though at a rate that might eventually slow down or accelerate depending on the role of dark energy. Yet, even this seemingly simple observation opens vast avenues of inquiry. Is the universe truly flat on scales beyond the observable horizon? Or does it curve in ways we cannot yet detect? And if so, what would that mean for the ultimate fate of the cosmos? The cosmic microwave background (CMB) is another critical tool in exploring the observable universe. This faint glow of radiation left over from the Big Bang permeates the entire cosmos and offers a snapshot of what the universe looked like when it was just 380,000 years old. By studying tiny temperature fluctuations in the CMB, scientists can infer a wealth of information about the early universe, including the distribution of matter, the rate of expansion, and the initial seeds of galaxy formation. These insights help anchor our understanding of cosmic history, but also raise questions about what came before. The period known as cosmic inflation, a rapid expansion in the first fractions of a second after the Big Bang, remains one of the universe's most mysterious chapters. If we could observe gravitational waves or other relics from this era, we might unlock secrets that go beyond the observable universe itself. The study of cosmic inflation leads to even more speculative ideas such as eternal inflation, where pockets of space continue to undergo inflationary expansion, while others like our observable universe stop inflating and evolve into isolated regions with their own physical laws. This theory feeds directly into the multiverse hypothesis, suggesting not only multiple universes in parallel but an infinite ensemble of universes, each with unique properties. In this view, our universe might be just one bubble in an infinite cosmic foam. Though such ideas remain unconfirmed and perhaps unconfirmable, they continue to inspire theoretical work and philosophical contemplation. In tandem with these theoretical pursuits, observational astronomy continues to achieve incredible milestones. Instruments like the James Webb Space Telescope and its predecessors, such as Hubble, have allowed astronomers to look not only further in distance, but deeper in time. Webb's ability to see in the infrared spectrum makes it especially suited for peering through cosmic dust and observing the early stages of star and galaxy formation. It has already revealed ancient galaxies that appear more mature and structured than expected, challenging existing models of how quickly matter coalesced into complex systems in the young universe. One surprising discovery is the presence of massive, well-formed galaxies that existed just a few 100 million years after the Big Bang. These findings suggest that galaxy formation may have occurred far earlier and more rapidly than previously thought, forcing cosmologists to revisit and revise their models of structure formation and question whether there were unknown mechanisms at play or whether our understanding of dark matter and its role in cosmic evolution needs to be refined even further. Such challenges to existing models underscore the dynamic and self-correcting nature of science. Every time observations conflict with predictions, they force researchers to reconsider assumptions, refine theories, and search for new explanations. In the case of unexpectedly mature early galaxies, scientists have proposed several possibilities. Perhaps star formation was far more efficient in the early universe than models suggest, with dense gas clouds collapsing rapidly under gravity to form stars and galaxies in surprisingly short time scales. Alternatively, there could have been processes at work, such as interactions with dark matter or even exotic physics, that accelerated structure formation in ways not yet fully understood. These questions highlight the profound complexity of cosmic evolution and the need for both improved observations and innovative theoretical frameworks. Meanwhile, The quest to understand the universe's ultimate fate is closely tied to these inquiries into its early history and structure. The role of dark energy in driving the universe's accelerated expansion is a particularly compelling area of study. Current observations suggest that this mysterious component makes up about 68% of the universe's total energy content. Yet its true nature remains one of the greatest enigmas in physics. Is dark energy a constant property of space itself, as Einstein's cosmological constant would suggest, or does it evolve over time, potentially growing stronger or weaker? The answers have profound implications.